Today we're going to be looking at more triangle congruence with a few more congruence rules. And our objective today is, again, I can determine whether two triangles are congruent in 2 out of 2 problems. So this is the same objective as in the last lesson. We're just going to expand on it a little bit. So to start off with, let's talk about some geometry conventions. We might have mentioned these in the last lesson or earlier in this unit, or these might be new to you. Either way, let's just make sure we're clear on what these conventions are. So first off, when we're naming polygons, we have to name the vertices in order. You can start with any vertex you want, and you can go in any direction you want. You could go this way. You could start with C and go B, A, E, D. That would be a valid name for this polygon. You could start with E and go E, A, B, C, D. That would also be a valid name. All of these names listed here are valid names for this particular polygon. You just have to make sure you go in order. So you couldn't go C, E, B. That wouldn't be valid because that isn't the order that the lines go in the polygon, the sides. And remember also when we're naming congruent shapes that the order matters. You need to name the corresponding parts in the same order in triangles. And speaking of corresponding parts, let's talk about a few congruence vocab terms. So remember, congruent means that objects are the same size and the same shape, but they could be in different places. We could have rotated them, we could have reflected them. So the orientation could be different, the location could be different, but they are the same size and shape. A rigid transformation is a transformation that produces a congruent image. So same size, same shape, but moves it somewhere. We call these translations, reflections, and rotations, or different variations of rigid transformations. And then corresponding parts we talked about a little bit in the last lesson. Those are sides or angles, or we could even say or points, that lie in the same relative position of congruent or similar shapes. So we would say this point moved to this point over here, and that would make it a corresponding part. This line segment moved to this line segment over here. That makes it a corresponding part. So let's just look at an example of corresponding parts. If you look at this diagram down here, these two shapes have a lot of congruencies marked. What are the corresponding parts? What's the corresponding part to angle A? Well, you can see angle A has a single arc and angle F has a single arc. That means that those two angles are congruent. And you can see this looks like a translation. This looks like it just moved over to the right. So A and F would be corresponding parts. So we write angle F is a corresponding part here. How about angle I? What's a corresponding part to angle I? Well, angle I has 1, 2, 3, 4 arcs. And over here, angle D has 1, 2, 3, 4 arcs. Notice it doesn't matter if we go to the before or the after. These are just a pair of corresponding parts. So we would say angle D corresponds to angle I. Now how about line segment HI? This line segment right here. Well, it corresponds to this line segment here, CD. And finally, line segment AB, what does that correspond to? So AB, line segment AB is right here, corresponds to line segment FG up there. So that's what we mean when we're talking about corresponding parts. Now here's a warning on geometry tests, standardized tests, anything where they bring up geometry. You will see this note probably, something like this. Figures are not drawn to scale or something similar to that. And the reason that is put on tests is because they will intentionally draw things that look non-congruent when they are congruent and vice versa. So they will intentionally draw pictures to mislead you. They want to know if you are paying attention to the congruent symbols, to the things that are stated in the problem. And so they will actually draw the pictures to make you think different than what is actually true. So you need to pay attention to what you can and cannot use in these problems. You can use what's stated in the problem, what's marked on a picture, and postulates and theorems that we've talked about previously in class or in math textbooks. But things you cannot use are, you can't just say things look the same. You can't use that as a valid reason to believe things are congruent. You also can't use things that make sense but are not yet proven. You have to actually prove them first before you can use them. All right, so with that in mind, let's talk about some congruent triangles. How do we know when triangles are congruent? We talked about this a little bit in the last lesson. And we asked, do we need all 6 congruences, as in 3 sides and 3 angles, or do we only need some of those? And we decided, actually, we only generally need 3 corresponding congruent parts. But it does matter which ones in what order. So this is a summary of what we found in that lesson. These 3, SSS, angle, included side angle, SSS is side, side, side. This is angle, included side angle, and side, included side, side, included angle, side. All 3 of those guarantee congruence. We said AAA, if you'll recall, that one scaled up and down, it was a dilation. AAA guarantees similarity, but not congruence. And SSA didn't guarantee either one. Do you remember why SSA didn't guarantee congruence? If you'll recall, one of the legs could swing one of 2 ways. So SSA guarantees one of 2 triangles, but we don't know which one. So it does not guarantee a single congruence. So let's reinforce these ideas and get a little practice with identifying congruence in triangles. So we're going to go through a series of pairs of triangles, and you decide if these triangles are congruent. You're looking for one of these 3 rules, if they are congruent, or if you see one of these 2 rules, either angle, 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 or side, side, not included angle, that would indicate there's not enough info to determine that these triangles are congruent. So let's give these a shot. How about these 2 triangles? If you said ASA, you got it right. So we have an angle, an included side, and an angle. So that's the side between the 2 angles. And those are reflected in the second triangle. How about this one? This one is side, side, side. You can see here we have numbers instead of congruent signs, but that's okay. That's exactly what congruence means, right? They are the same length and for line segments. So this is still side, side, side. We have 3 sides that are the same length. How about this one? Can we prove that these 2 triangles are congruent? No, actually. So this is a side, side, and an angle, a side, side, and an angle. Remember, this is the one of 2 options. So we don't have enough info to say these are definitely congruent. How about this one? If you said side, angle, side, you got it. We have a side, an included angle, and another side. That's the angle in between these 2 sides. Similar up here, we have a side, and an included angle between them. Now notice in this particular drawing, this is an example of them trying to mislead us. These triangles don't look the same size at all. And if we got out a ruler and measured them, that would tell us that they probably aren't the same size. But we need to rely completely on these congruence marks. These congruent marks say they are actually congruent by SAS. How about these ones? That one might be a little bit easier to spot as AAA because we have 3 angles marked, 3 angles marked over here. But keep in mind that AAA does not guarantee congruence. Remember we said that could be dilated up or down, it could be bigger or smaller. All the side lengths could be changed even though the angles are staying the same. How about this one? This one's a little bit tricky. This one is SSS, side, side, side. So you can see we have a pair of congruent sides here, a pair of congruent sides here, and then they share this congruent side. Remember, we have that reflexive property that says a congruent side is, or a side is congruent to itself. Any object is congruent to itself. So that one is side, side, side. They are congruent triangles. How about this one? Here's another one where we have numbers instead of congruence marks. This one is angle, side, angle. You see we have 2 angles marked, those match. And then we have a side in between them, angle, side, angle. Are these triangles congruent? We can't say for sure, we can't say they're not, but this is side, side, not included angle. This would be the included angle, so this is the not included angle down here, or one of the not included angles. Over here we have side, side, not included angle. We said that one is not enough info to guarantee congruence. One more of these. Are these triangles congruent? They sure are. They are marked S, side is congruent, then an angle, then a side. This is the angle between the 2 sides. Again, we're using that reflexive property where this line is going to be congruent to itself. So good job on those. Think about how you're feeling about triangle congruence postulates. Maybe go back through them if you're not feeling great. And we will move on with more congruent triangles today. So here's our summary again of the congruent triangle rules we found. And there are some ways to remember this. Like SSS is pretty easy to remember because all those sides are locked into place. And then ASA and SAS, these are both included. This is the included side and the included angle. So we include them in our congruence rules. AAA we remember as our only similar one. That's the one we can scale up and down. And this one, SSA, one way to remember this is not a congruence rule, is that it's the only one that makes a naughty word that we shouldn't say in class if you read it backwards. So you can remember that's the one that we don't want to include in class and we don't want to include in our congruence rules. Now we're going to add 2 more to the congruence rules today, and we could have done these as postulates before. We could have experimented with them, explored to see if there was any possible way of making triangles, 2 different triangles with these rules. But I like to minimize the amount I need to memorize. So these 2 rules we're going to add today, we can actually figure out using theorems we probably already know. And so I like to leave those to remembering just how to figure it out rather than memorize them. If it works for you to memorize them, that's cool too. But I like to just memorize these 3 and then work from there. So in order to introduce our first one, we're going to review another theorem that you've probably seen before, but maybe not. If you haven't, that's okay. And this theorem is called the triangle angle sum theorem. And by the triangle angle sum theorem, that just tells us that the 3 interior angles of a triangle add up to 180. Have you seen this before? Maybe? We take these angle measures and we add them together and they will always equal 180. So true or false? If that is the case, if we know the measures of 2 of the angles of a triangle, we can always find the measure of the 3rd angle. What do you think? Is that true? That is true. Because if we know 2 of these angles, all we have to do is subtract them to find the third one. We get z equals 180 minus x minus y. So we just have to take 180 minus the two angles that we know, and we get the measure of the third angle. So let's take a look at a couple of triangles here. We're asking, are these triangles congruent? We have some angles marked, we have a side marked. What corresponding parts do we have? Well, let's see, we have two angles that are congruent. We have two other angles that are congruent. And then we have a side that's congruent. So this looks like AAS. Now we haven't talked about AAS yet. We don't know whether that one is or is not a congruence rule. But look at these triangles for a second and think about that triangle angle sum theorem we just talked about. Is there anything else you can tell me about these triangles that we can sort of deduce from that theorem? Maybe we can figure out the measure of this angle right here, this angle. Well, we said all interior angles of a triangle will add up to 180. So we know that 105 plus 40 plus this missing angle, maybe we'll call it A, is going to be 180. So we just need to subtract 105 from both sides. We get 75. And we subtract 40 from both sides. And we get A equals 35. So we can totally determine what this angle measures if we have the other two. But look at this now. Since these are the same measures, that means this one's going to be 35 degrees as well. And now we have angle, side, angle. This is the included side between these two angles. Down here we also have angle, included side, angle. So we already have now ASA, which we know is a valid congruence postulate. So we don't even have to prove AAS separately because it's equivalent to ASA. By this method, just find the missing angle, and then you have ASA. That missing angle will always be congruent if the other two are congruent, basically because of the subtraction property of equality. So when we have AAS, that's essentially equivalent to ASA. So AAS should be a valid congruence postulate. Now, what if we have congruence marks instead of numbers, though? Can we guarantee the same thing? Once again, this is an angle, and a side, but now we don't have numbers, now we just have markings. Can we still use that same reasoning? Can we still say this is congruent by ASA? Well, let's just give these angles variables, shall we? A, B, and C. This one's corresponding part is that one, so A. This one's corresponding to that one. And we'd want to know if both of these would have to be the same number. Well, we said A plus B plus C would have to be 180. We can subtract A and subtract B from both sides. And we get C equals 180 minus A minus B. So that's that value of C right there. We don't know exactly what the number is, but it is locked into place by the value of these A and B, which are set over here. So that means this one also has to be C because it has the same angles in that triangle. So C and C must be congruent as well. We could maybe do like 3 arcs here. They will be the same. They will be 180 minus A minus B. So now we do have congruence. We have angle, side, angle, congruence, and angle, side, angle. Yes. We can still use ASA to prove these triangles are congruent. So we're going to add that one to our list of congruence rules. Now remember, you can memorize this if you want to, or if it helps you, you can just reason out that it's equivalent to ASA using the triangle sun congruence, or the triangle sun theorem rather. All right, so now we have another theorem that may look familiar. This one's called the Pythagorean Theorem. And this refers to right triangles specifically. For any right triangle with legs A and B and hypotenuse C. So let's talk about what that means real quick. Legs of a right triangle, remember, is 90 degrees, is one of the angles. The legs are the sides that touch that 90 degrees. The hypotenuse is the side that's opposite the right angle, the side that doesn't touch it. And so we say for the lengths A and B and hypotenuse C, the legs A and B and hypotenuse C, then A squared plus B squared will always equal C squared. That's the Pythagorean theorem. So true or false, if we know two lengths of the sides of a right triangle, we can always find the third one. If we know two of these numbers, can we find this third one? Yeah, this is also true. Because once again, we're just solving for one of these variables. This is going to be a little bit more complicated than the last one where we just subtracted it from 180, but we can still solve this for one of these variables. Say, let's solve this for A. We just subtract B squared from both sides. We get A squared equals C squared minus B squared. We take the square root of both sides. We get A equals square root of C squared minus B squared, which is a little bit more complicated, but it still just evaluates to a number that is set. So yes, we can absolutely figure out the missing side if we have two of these sides. So let's see. We have two triangles here. We're asking, are these triangles congruent? What corresponding parts do we have? What do you think? Let's see, I see a right angle, so it looks like that angle and that angle. Then I have a side of 4, and then a side of 5. So this looks like an SSA. Side not included angle. See how these two sides are together? This would be the included angle. This is a not included angle. So side angle, did we say that was a valid congruence postulate? No, that one was the naughty word that we leave out. So SSA is not a valid congruence postulate. However, we do have some special information here. This is our right triangle. So is there anything else we can figure out about this triangle? Maybe having to do with that Pythagorean theorem we just talked about? Well, what if we make this unknown side, we call it A, we call it length A. Then we would know that the lengths squared and added together equal the square of the hypotenuse. So A squared plus B squared, we're going to call that 4, equals C squared, which is 5. So this is just A squared plus B squared equals C squared. We don't know what A is, but we know what B and C are. So 4 squared is 16, 5 squared is 25. And then we can just solve this for A. We subtract 16 from both sides. We get A squared equals 9. Square root both sides. We get A equals 3. So the fact that this is a right triangle means that if they give us two sides, we always know what the third side is. And look at that now. Now we have another side. We have a side congruence. SSS. We know for sure that one works. Side. So effectively, SSA with this right triangle is equivalent to SSS, side. Now once again, we need to consider, do we need those numbers or can we just use those congruence marks? Well, we could just give these labels like this, A, B, and C, A, B, and C. So these congruent sides are set. We know that they're equivalent, but we have this unknown side, and we know that A squared plus B squared equals C squared. So our unknown here is B. We can solve for that. We get B squared equals C squared minus A squared, and now we just have that last step to square root to get B by itself. We get B equals the square root of C squared minus A squared. So once again, this is just a set number. We don't know what the number is, but we do know that both of these B values have to be the same. They have to be this value right here. So we can determine that these sides are also congruent. So yes, we can again use side, side, side to prove that these triangles are congruent. Now you'll notice here what they provided us was the hypotenuse and a leg. So this rule is known as the hypotenuse leg theorem for triangle congruence. If they give us a congruent hypotenuse and a congruent leg of a right triangle, even though this technically is SSA, this special case of SSA does mean they are congruent. This is hypotenuse leg. So we're going to add that to our list as well. Hypotenuse leg is a valid congruence rule, but remember, it only works for right triangles. So we're building up our geometry toolbox now. This is what we have so far. We have this list of triangle congruents. AAA is similar, SSA doesn't work. We also talked about the triangle sum theorem today and the Pythagorean theorem. And previously we have also talked about corresponding parts and the reflexive property, and the object is congruent to itself. So we have all of these things in our geometry toolbox we can use to prove shapes are congruent. So that's everything for today. We are going to use these rules, use these tools that we have on our assignment, and determine whether two triangles are congruent in 2 out of 2 problems.